Hello and welcome to this 15-minute online presentation on our conference contribution titled Tracer-Based 3D Surface Reconstruction in the framework of the International Symposium of Particle Image Symmetry. My name is Constantin and I'm looking forward to guide you through this presentation. For now, I will disappear. See you at the end of the presentation or in the Q&A session. So let us start with this photograph of the velocimetry measurement on a full-scale cyclist that we have done in our wind tunnel facilities in Delft. Why should we need a tracer-based interface detection method? Well, in fact, part of the geometry is unknown to us. So in this specific case, we didn't have the geometry files of the bicycle and the helmet, which were not released by the manufacturers. On top of that, we have assembly tolerances from placing the model onto the bike, but also placing the helmet onto the model. This introduces mechanical loads as well, which can result in model deformation. In your case, you may have aerodynamic loads, which also cause a displacement or deformation of your model. Secondly, we are often interested in surface flow properties, such as pressure. So here we were actually looking for the surface pressure distribution on the model. It is clear that you will need the surface geometry to do so. Now, if you do not have a 3D scanner or digital image correlation or any likewise system at hand, or if your model does not allow to use such system for scanning the geometry, you are stuck with getting the surface geometry from your flow measurement or relying on a predefined geometry. Even if you have the tools available, you still have to match reference frames. So we were asking ourselves, aren't the flow traces providing enough information to reconstruct the model geometry? And that's what we are going to answer in the remainder of the presentation. So what is the principle of interface detection that we thought of? Well, let's simplify everything for now. Let us look at a planar case of a flat interface that is infinitely thick, and further let us model the particle distribution as a continuum. Now what we can see is that the fluid phase on top of the model surface, well, that's seeded, whereas the solid phase is void without particles present. So we have to find the interface of those two phases. On the left hand side you see a point A, which is our assessment point, around which we span a surge segment of radius r indicated in blue. Now what we will be analyzing is the mean position of the tracer particles in this blue circle against the center of the circle, which will be a vector, and we are analyzing the vector magnitude. So in this particular case, the two positions should coincide, so the vector magnitude should be 0. As we approach the interface, part of the circle will coincide with the solid, and consequently no particles will be found in this segment, now indicated in gray. Therefore, the vector magnitude of the mean particle position and the circle center will be non-zero. As we get closer and into the surface, the vector magnitude will keep on increasing until we do not find any particles anymore, as we are fully immersed in the solid. As such, situation C, where we are coinciding with the assessment point and the fluid-solid interface, can be associated with interface detection. The vector magnitude we expect to see if we assume the fluid phase is continuously seeded is 4/3 pi, which can be derived and is done in the paper. So we can associate this value with interface detection. And we can use this approach in a systematic manner by computing the vector magnitude on a structured grid and extracting the isocontour of the critical displacement. And this will give us an approximation of the fluid-solid interface. Now, I summarize this principle in a flowchart on the right, which I will not discuss any further in view of time, but I really want to reiterate our model assumptions up to this point. So far we have assumed a flat and thick model interface, a continuous particle distribution, and a planar case, so 2D data. Now this will raise a number of issues, namely what happens if we look at curved and thin geometry, what happens if we look at discrete particle data as we are used to in PIV and PTV, and can we extend this model to 3 dimensions. So let us start with curvature. Let's assume we have a convex shape of constant curvature radius ρ. On top we have the fluid domain and on the bottom we have a solid. Our model assumptions are a flat and thick interface with a continuous data distribution in a 2D case. What are the consequences if we analyze a point Ci located right at the interface? Well, our model expects to see the following: a semicircle of radius r with a mean particle position or center of mass at a location Xi, 42% of the radius away from the base. However, we are ignoring the fact that there might be particles in the purple region due to the convex shape of the interface. This part of the search segment will pull the centroid closer to the surface, and therefore the centroid of the convex shape is smaller than that of the flat interface. If we stick to our 2D and flat model assumption, we will be eroding the interface. Now, we can repeat the exact same analysis for a concave interface, and you will not be surprised to see exactly the opposite trend. So now the center of mass of the concave case will be further away from the interface as in the case of a flat interface. Consequently, we are dilating the interface. If we quantify this error, we get the following curves for convex and concave cases, where we have normalized the surface curvature radius ρ by the search segment radius r. If we stick to our assumption of a flat interface, so we use the critical value of 4/3 pi indicated by the black dashed line, we will get the following error in the reconstruction, again as a fraction of the search radius r. You can already see that even if the surface curvature radius is only 2 times bigger than our search radius, the error is still smaller than 10% of the search radius. And for the case where this curvature radius is 4 times bigger than our search radius, the error drops below 5% r. And in fact, we do not really need to worry about this as long as we can satisfy this condition. Even if you think this is critical, you could use this information to apply a correction, which we are not doing. Let's move to a numerical example of an airfoil case, which is a challenging geometry because it has various curvature from convex to concave shapes and a very thin aft section. So far we have assumed a continuous data distribution, which is not representative of particle image velocimetry. So what happens if we look at discrete data? What are effects of sample size and tracer concentration? We will be looking at this using the error matrix of the maximum and mean positional error of the reconstruction with respect to the known reference model geometry. So let's take a look at the variables that we will be using to quantify our metrics. We have the tracer particle concentration indicating the number of tracers per unit area. Instead, we will be quantifying the concentration level in terms of interparticle distance lambda, which is inversely proportional to Cp. For the instantaneous case you see on the right, the mean interparticle distance is 1% of the chord length c. For the time average case, we will be considering the equivalent of 100 of those images. We quantify the sample size with a variable k, which describes the mean number of tracer particles we expect to find in a semicircle at a flat interface. K is directly proportional to Cp, or the square of the search radius, which is an indicator of our search area. And in fact, the radius is our control variable in which we can manage the size of k. So how do instantaneous and time average case compare? The instantaneous case is represented by the blue data, whereas the time average case is represented by the orange and red data. Comparing the y-axis, you see that there's an order of magnitude difference in the error. For small sample sizes, below 10, we see that the error is dominated by random error. The sample size is statistically insignificant and we get a large random error. On the opposite end of the scale, we run into issues of truncation, where spatial resolution becomes an issue. So let's take a closer look at the specific case of 30 samples in the instantaneous case. From the particle distribution, we get the centroid shift map on the bottom. Note here that the shift map is quite noisy, and in fact we could regularize this using a sliding regression. We are not doing this here, but you can see the effect of the regression in the full paper. We normalize the shift map by the critical centroid shift value of 4/3 pi, such that the unity contour in the shift map gives us the reconstructed interface, which you can see on the top right. What you will see here is that for the body of the airfoil we do a very good job at reconstructing the geometry on both sides, the suction side and the pressure side. Instead, the trailing edge is completely missed, and also the leading edge is somewhat eroded. And the reason for this is that the size of the search segment, which is indicated here, is much bigger than the thickness of the airfoil in these regions. Therefore, we run into issue of truncation error, which is of course to be avoided. As you can see in the error metric over the chord lengths, the leading edge and trailing edge are the region of maximum error. However, in between, even with this coarse analysis volume, we reach error levels below 2% of the chord lengths. Instead, if we look at tracer concentration, we can already compare the instantaneous and the time average case, where we saw that there's an order of magnitude difference in the error magnitude if we consider 100 instead of one image. So here you indeed find the linear scaling between the interparticle distance lambda and the maximum and mean error matrix. So the more particles you have, the better the reconstruction accuracy. So let's summarize the numerical example. We have seen that curvature is not an issue if our curvature radius is greater than 4 times our search radius. Likewise, finite thickness is not an issue as long as our thickness or minimum thickness is greater than our search diameter. The sample size k is a trade-off between random error and truncation error. For the specific case, the optimum sampling size is about 20 particles in a semicircle or 40 particles in a full circle. We saw that the maximum error is about 10 times our interparticle distance for this specific example. And what we didn't see, but you will find this in the full paper, is that our error can be reduced by approximately 25% if we apply a linear regression to the centroid shift map. So what's left? Well, we want to extend the theory to 3D, and we also want to use a real experimental case to validate our model. Let's start with a 3D case. In fact, all we need to do is we need to change from a circular search area to a spherical search volume and repeat our analysis. What we find is that the characteristics are very similar. The centroid shift in the continuum limit as function of wall elevation h is slightly different, but it still increases monotonically, and we just need to update our critical value from 4/3 pi to 3/8. So let us take a look at an experimental case. Here we will be using the measurement of a coaxial volumetric velocimeter on a truncated cylinder model. And we will be asking ourselves, is the particle distribution sufficient to get a geometry reconstruction like you see on the right-hand side? The input data was kindly provided by our colleague Eduardo, who in fact published this experimental dataset already in the Journal of Computers and Fluids. Here you see the setup again of the 10 cm cylinder analyzed by the CVV system. On the right-hand side you see the particle distribution, and you see a number of experimental errors. And we do not want to hide those, but we want to test what is the limit of this reconstruction method. Here you see the shadow caused by the cylinder. Point B is indicative of a reflection on the model where we cannot reconstruct particles well. Point C shows where we had a more functioning nozzle and we had a lower concentration of tracer particles. D is the edge of illumination, and in point E you will find a number of ghost particles inside the model. So how do these imperfections affect our geometry reconstruction? Let's take a look. Here we see the reconstruction we get if we use a search radius of 10 millimeters. So we are analyzing particles in a sphere of 2 centimeters diameter. Note that the model radius is 50 millimeters, so they're almost on an equivalent scale. We colored the reconstruction by the reconstruction error. And you see that for the majority of the model, the reconstruction error is within 10% of the model radius, so within 5 millimeters. As expected, the convex edge of the flat model back to the cylindrical and spherical upper section is eroded, whereas at the interface to the floor, which is a concave edge, we are dilating the model. The main error you see is from the ghost particles inside. Now it is clear that with our approach, you should make sure that you do not get particles inside the solid model. Otherwise, we get a very good reconstruction within the expectations of our model. So let us summarize. What have we seen? The tracer-based 3D surface reconstruction utilizes the fact that we can discriminate between a seeded fluid phase and a void solid phase. To find this interface, we analyze the spatial distribution of tracer particles in an isotropic search volume. Therefore, we do not require any velocimetry data, but only particle positions. The selection of the search volume is a trade-off of random error and truncation error. We have derived the principle for a flat and thick interface in 2D. We have analyzed curvature effects, and we also showed limitations for finite and thin objects on the synthetic airfoil case. The extension to volumetric data was straightforward, and the application to experimental data showed that we get a shape reconstruction within the resolution of our fluid flow measurement. If you like this presentation and want to find more details, please take a look at this publication, which is already available in open access. Now with that, I would like to finish the presentation, and I look forward to answer your questions in the Q&A session. See you there.